Hi, so in the last class I talked about Joule-Thomson expansion process or Joule-Thomson throttling, and I told that Joule-Thomson expansion coefficient for uh, ideal gases is 0. But there is this process called reversible adiabatic expansion that you will often come across, right? That is something that is used in different heat engines. Although heat engines may not seem very important for thermodynamics of materials, but it is very important to understand these adiabatic processes because you have adiabatic processes, isothermal processes, isochoric processes, isobaric processes, and here I am talking about adiabatic processes. And when a gas expands in an adiabatic process, what really happens, right? How does the temperature relate to the volume, etc. So you see, when you have reversible adiabatic expansion, reversible means that it is the process is infinitesimally slow, and basically you can plot it on a PV curve. Say for example, if I have a PV curve, then I can. So say for example, this is pressure, volume. Then you can basically draw some sort of a curve like this. Right? It is represented. This curve basically tells me that something is like Vibhuti Bar. Say for example, this curve is like PV power gamma equals to constant. Now, what is this gamma? Right? So, and how do you determine this gamma? So, for that, say for example, this is the equation of an adiabatic process or a reversible adiabatic expansion of an ideal gas. So, let us consider first an ideal gas of an ideal gas. So as soon as I tell ideal gas, what comes in mind? A constitutive, a state relation, a relation between the states, an equation of state. That's called an equation of state. Whether it's an ideal gas or a real gas. For example, Van der Waals equation of state, you will see in one of the assignments, I have talked about Van der Waals equation of state. So, equations of state basically relate in general, it relates the intensive variables and extensive variables. Say, for example, for ideal gas, the simplest equation of state that we know for quite some time is PV equals to N R T, where N is the number of moles, P is the pressure, V is volume, R is universal gas constant, and T is temperature. Now, when I talk about adiabatic process, then or adiabatic expansion, then first thing that comes in mind is that delta Q has to be equal to 0. As you can see here, that I have noted here, that delta Q is going to be 0, right, for an adiabatic, because the process is adiabatic. Right, because it does not allow any heat exchange between the system and the surroundings. Right, now delta Q equal to 0, delta W equals to minus PdV, and this is something that this is delta again. This is reversible mechanical work. It is minus PdV. Whether work is done by the system or work is done on the system, based on our convention of work done on the system is positive. Delta W. So whether it is by the system or on the system, delta W is always minus PD, right? So in one case, for example, if it is on the system, P basically is the external pressure, denotes the external pressure, and dV denotes the decrease in volume, right? So that's negative. So that's why I put a negative sign. On the other hand, when you tell that work is done by the system, the gas is expanding against some pressure. So if it is against some pressure, again, the internal pressure is like minus P, and minus P into dV, where dV is positive. Right? So in both cases, the equation is minus PD. Right? It's force displacement relation. And then you have also change in internal energy of the gas that is expanding, which you can write as CV. CV is the heat capacity at constant volume, dT. Right? This is heat capacity at constant volume. Remember, this is not the molar heat capacity, but it's the total heat capacity at constant volume for some n moles. Now, if it is so, according to first law, now if I use first law, next page, if I use first law, then we can directly write du equals to delta q plus delta w. Again, why delta? Delta is because it's a path function and this is all reversible. So let us write delta q rare, delta w rare, and this is cv dt, and this is 0 minus p pv. Now the equation of state is pv equals to n t. Now therefore p I can write as nRT by v. And see, P is not, so instead of P, I am substituting as nRT by V, and P is the external pressure or the internal pressure, which is then we can write CV dt equals to minus nRT dV by V. Or we can also write further CV dt by t. I am taking t this side. I am taking this t this side. So it becomes CV dt by t equals to minus nr dv by v. Now I can integrate. So I am integrating and say I tell that initial temperature was Ti, final temperature is Tf, and similarly it is Vi and Vf. Then what do I get? I get Cv ln Tf by Ti equals to minus nr ln Vf by Vi, or I can write as nr ln, I put the minus sign, so Vf Vi by Vi to the power minus 1, right? So it is basically ln Vi by. Now we will continue with this relation. So Cv, now we can write nr by Cv. So basically what we can write is ln Tf by Ti equals to, let us put some number, nr minus nr or nr by Cv. Okay, nr by Cv. So here this is nr by Cv ln Vi by T. Okay, so now this nr by Cv, as you can see, n is the number of moles constant. Let us assume it to be constant, it doesn't change, and R is gas constant, and Cv is the molar capacity. Obviously, it can be a function of temperature. Cv can be a function of temperature, but we can also assume it to be a constant. Now, in such a case, what you have this, right? You got this Cv ln Tf by Vi plus minus ln Tf by Vi, which is basically nr ln Vi by V. Now, what you are writing is chi. See, I can also write it as gamma. Some textbooks use gamma. I prefer to use the word chi, right? Because I don't want to confuse gamma with something else. So later, so I use the word chi, the symbol chi, and sometimes people do use gamma. It's like new. I'm very sorry for this. Let us call it gamma. Okay, and equal to Cv by So in here we will call it as chi. Let's call it chi. So if you see that, so Cv by nr, nr by Cv. So I just write Cv by nr ln Tf by Ti equals to ln Vi by Vf. Now see, this can be written as Tf by Ti equal to Vi by Vf whole to the power Cv by nr. Now this CV by NR I am replacing by the CV by NR that is there in the superscript. This is there in the superscript here. The CV by NR I am replacing it by gamma, the symbol gamma or the symbol chi, one of them. So I am using here chi, for example, as you can see here chi, and then what happens? TF by TI. So am I correct? This is not correct. This has to be TF by TI whole to the power TF by TI whole to the power CV by NR equals to VI by VF, or you can write as TF by TI equals to VI by VF whole to the power the ulta thing, that is NR by C. NR by C. Right? This is also possible. So both ways we can write. So this is CV by NR. The way I have taken is NR by CV I took here. So this one, this branch came from this, and this one is following from this way of rearranging. Right? So both ways we can write. So let us follow one of the ways and see. So you have chi ln TF by TI, CV by NR. So basically here is CV by NR, and here you have VI by VF. So TF by TI to the power chi, right? Where chi equal to CV by NR is equal to VI by VF, or TF by TI equals to VI by VF for 1 by chi, right? It is 1 by chi, because if you see, this is CV by NR if it's on the left hand side. If it's on the right hand side, it is NR by CV, right? It has to be NR by CV, because what I'll do here, I will use this expression. When I put NR by CV on the right hand side, then NR by CV. So VI by VF will be called NR by CV. And if I put it on the left hand side, then it becomes CV by NR, right? So both are possible, and as you can see here, TF by TI equal to chi equal to VI by VF. You can also write as TF by TI equal to VI by VF equal to 1 by chi. This is something that you have always done. And now you see TI by TF is VF by VI. Now this is one interesting. So if I now create a reciprocal of both terms on both sides, then this is TI by TF is 1 by TF by TI. So, and this also becomes 1 by VI by VF whole to the power chi. So it becomes VF by VI whole to the power, right? Now, so I will not call this gamma. I will call gamma as, so here we will call gamma as Cp by Cv, chi as Cv by NR. Now you see Cp minus Cv equal to NR. This is for ideal gas. This we have already shown. For ideal gas, Cp minus Cv equal to NR. This is something that we have already proved. And then we are writing gamma equal to Cp by Cv. Now is equal to C Ti by Tf equals to Vf by Vi to the power NR by Cv. Now NR by Cv, you have NR here, as you can see, you are substituting NR, you substitute NR by Cp minus Cv. So it becomes Vf by Vi whole to the power Cp minus Cv by Cv, which is Vf by Vi, Cp by Cv minus 1, which is basically Vf by Vi to the power gamma minus 1, right? So it becomes to the power gamma minus 1. Now what is the relation between chi and this? So chi equal to, look at chi equal to, let's use another color. Chi equals to Cv by NR, right? Cv by Cp minus C, and which is basically Cp minus Cv by Cv whole to the power minus 1, which is equals to Cp by Cv, which is gamma minus 1 whole to the power minus 1, or which is equals to 1 by gamma minus 1, right? So if that is so, now another thing, Pi by Pf equals to Vf by Vi. That is something that you can also use, right? Pi by, so if that is so what did I do? I have written here, it has become clumsy. So let's look at this. Yeah, so you have say PV equals to nRT. So if I write this way, Pi Vi equals to n, say if I keep the constant Pi, and Pf Vf equals to n Pf. So Pi Vi, therefore one can write Pi Vi by Pf Vf equals to Pi by Tf, or you can write Pi by Pf equals to Vf by Vi into Pi by Tf, which is basically, again we have found that Pi by Tf is nothing but Vf by Vi to the power gamma minus 1, right? Vf by Vi to the power gamma minus 1. Now you have Vf and Vf to the power gamma minus 1, which gives you Vf to the power gamma and Vi to the power gamma. So it means it basically tells you Pi by Pf equals to Vf by Vi to the power gamma. So now if you do that, so it becomes Pi Vi to the power gamma. See, if you rearrange now, it is Pi Vi to the power gamma equals Pf Vf to the power gamma, which is a constant. This is for, so basically if I write such a process, this is a process that I will use. If I use such a process, this process that you are seeing here, I will come a little back and show you that this process that I have represented here on the PV is a reversible. By the way, if it is reversible, it is not possible to put this path in a PV diagram, because at each point in this path, right, at each point in this path, the system can traverse this path both ways. Means it can go this way, it can go also the other way, and the way it is happening, right, at each point of increment, I come here, allow it to equilibrate, come here, so it's an infinitesimal process. But as you can see here, that for reversible adiabatic expansion, the work done is PV to the power, right? So basically not work done, the work done is minus PdV, but what you get is PV to the power gamma is equal to constant. So for a reversible adiabatic expansion of an ideal gas is represented by an equation of state of the form PV to the power gamma equals to constant, where gamma equals to Cp by Cv. Remember, gamma I am using here as Cp by Cv, and Cp minus Cv by Cv is where I am, or Nr by Cv is what I am using as guide. Okay, so now we know adiabatic process, we know also isothermal process. We know isothermal process. For isothermal process, temperature is fixed. Isothermal temperature does not change. T is same. So there it will be Pi Vi equals to Pf Vf equals to K. So in one case K1, so K isothermal. So let's call it, and here it is like Pi Vi, Pf Vf equals to, you can write this P also. This is Pi Vi to the power gamma equals to Pf to the power gamma equals to P to the power gamma equals to K. Right? Yeah, so these are the two equations of two equations representing isothermal and adiabatic process. Right? Isothermal for a given temperature T, and adiabatic for in case of adiabatic, what am I keeping fixed? I am keeping nothing fixed, right? Temperature is changing, your pressure can change, your volume can change, right? So basically, you can. However, if the pressure, so pressure, so you have PV by T, right? So the relation. So pressure, volume, temperature, all constant. So you can write in one case PV by gamma, where gamma is Cp by Cv. In other case, gamma there is no gamma. Okay, now I come to a very important law. It's called the second law of thermodynamics. Second law of thermodynamics is very fundamental because it is not the principle of conservation of energy. Second law of thermodynamics does not teach you the principle of conservation of energy. It teaches you directionality. It tells you that there exists a property of the universe. The universe is composed of system and surroundings that will change in a certain way or in a certain direction, irrespective of whatever process takes place. Irrespective of whatever process is taking place in the universe, this property called entropy will change in a certain way. So now, as you can see, there are two types of processes, right? One is called a natural process or a spontaneous process, that does not require work to be done on the system, right? The spontaneous process does not require any work to be done on the system. So that's called a spontaneous process. Think of a spontaneous process here. For example, free expansion of a gas. So you have kept a gas in a chamber. So in one side of the chamber you have kept a gas, in the other side you have kept vacuum, or you have created a vacuum, and the chambers are separated by a valve, and the valve is closed, so that the gas cannot basically flow from the left chamber to the right chamber. So in such a case, if I open the valve, what will happen? There will be a free expansion of gas. There is no work. So gas will automatically go and fill the chamber that was having initially vacuum, right? So, and it will go on filling, and you will see surprisingly that at one point of time where it has completed, so you will see that the filling has happened spontaneously, right? It has happened spontaneously because there was no work that has to be done for this gas to flow through the open valve into the chamber that contains vacuum. This is an example of this free expansion. So example here, if I have to give, then I can tell. One major example that I can give is free expansion of a gas. Okay, so because there is no work required to be done for this free expansion of the gas. Then there are also non-spontaneous or artificial processes. For example, in a hot summer day, when you run your AC, the AC is cooling you, but AC is also releasing a lot of hot air outside, and the work done to cool the room is non-spontaneous or artificial, right? So there are such processes. One is a natural process. Another example of natural process, I have a hot body and I have a cold body. I put them, and say for example, I put them together. You will see that there will be heat flow unless till there is an equilibrium. That is all the thermal equilibrium. Thermal equilibrium means there will be some intermediate temperature at which both bodies will settle. Right. So, and this heat flow that will happen is again from hot body to cold body. You will see later that it's a natural or a spontaneous process. Non-spontaneous is if the heat had to be made, means if we could use a mechanism to make the heat flow from the cold body to the hot body. For example, when I am talking about air conditioning, see, you have a very hot summer, think of that. So you have the surroundings, so you are sitting in a room and the surroundings is really hot, like 40 degrees Celsius. Inside, if you do not have any air conditioning, your temperature also has to go towards, say for example, it's like the surroundings is everywhere is 40 degrees Celsius, a huge volume surrounding. So ultimately, the room temperature should also settle to something like 40 degrees Celsius. right? So in contact with the surroundings. However, when our AC is running, there is some work that is done so that the cold room can reject heat and to the surrounding, which is already hot, right? The cold room can reject heat and the room remains cold because of the machine, right? So this is a colder room, a cooler room. You can maintain a cooler room by doing some work, and that is where, so there is some work done, and therefore this process of air conditioning is a non-spontaneous or an artificial process. Now, all these natural and spontaneous processes have some spontaneous process has a direction, non-spontaneous process or artificial process has a direction. Now, all these processes follow second law of thermodynamics. Second law of thermodynamics, again, to recap, is the property of the universe, and that property of the universe changes in a given direction irrespective of the process that is taking place. Dynamics. Now, this is very interesting. So, the way I want to define it is like that in second law, you get a state function, right? You define a state function called entropy. Now, note that in second law, you are not, in the first law, you defined something called energy and you told energy is conserved. Now, you are defining something called entropy, but you are not talking about anything about the conservation of entropy. What you are telling is that S universe or S total always increases in the direction of spontaneous change. You are telling, what we are telling is S universe or S total always increases in the direction of spontaneous change. Right? So, in the direction of spontaneous change, the S universe or total entropy of the universe should always change in the direction of spontaneous change. So, delta S universe has to be greater than 0 for any spontaneous change. Now, as you can see, if I look at delta S, it is like a macroscopic change, a change that is measurable, and ds is an infinitesimal change. So, often as you have seen previously, delta will be used for a macro change and means a measurable change, and d for infinitesimal changes in the entropy. Now, think of this. There is, as I told you, that there is a delta S universe, right? There is a delta S. And it is always greater than 0 for a natural process. Right? And we are telling now that this delta S universe or delta S universe is a sum of delta S system, right? There is delta S universe, you can write as delta S system plus delta S surroundings, right? So, it is delta S system plus delta S surroundings. Let's call it delta S surroundings. So, it's like I just write SUR. So, SURR basically denotes surroundings. However, for each case, what we are telling, for each part of the universe, that is system part of the universe, that is the system is the part that we will be focusing on, or the surroundings part of the universe can be divided into two further terms. One is called entropy transfer between the system and surroundings. Because of the heat transfer that happens between the system and the surroundings, there is something called an entropy or a state function entropy that transfers between the system and the surroundings, and we call it delta S T, small t. Delta S with a subscript of small t basically denotes the entropy transfer between the system and surroundings because of exchange of heat between the system and the surroundings. However, there is another term which is called delta SP, which is our delta entropy production term, and this entropy production term is always going to be greater than 0 as long as the process is spontaneous or natural. The delta S production can go to is always going to be positive, or it can also be equal to 0, but it cannot be negative. On the other hand, delta S transfer can have any sign. Delta S production is always going to be either positive for natural or spontaneous processes, or it can be also 0. So now we have to understand what does entropy production mean. See, there have been a very nice understanding and of physical phenomena, and the understanding of physical phenomena is what led to this definition of entropy. Once you can define entropy, you find that it becomes very useful. This property called entropy becomes very useful to understand the directionality of a process and to qualify the process as spontaneous or non-spontaneous, right? And so that is very, very important, and that was very clever way to define entropy in addition to energy. Now think of this. Think of an example. So spontaneous process means it's a natural process. Now what I am trying to say, a natural process is irreversible. For example, let us think of a very simple process of a growth of a plant. So a plant grows into a tree. So you first plant a seed and you give water and nutrition from sunlight and all comes, and then the seed starts. So it's called germination process. And you have the seed, and then the seed suddenly gives rise to a very small plant, and then the small plant has some leaves, and the plant continues to grow, and finally it becomes a full-grown tree. But the tree itself, now if I think of the process in reverse, that there was a big tree, and the tree is shrinking down to the seed. That is not going to happen. However, the seed becoming bigger in the form of a very big tree, say for example, is a natural process. But if I have to take that big tree and convert it into a seed, then it has to be an unnatural process, and how much of the energy or work that I have to put in, I really do not know. But we can measure it. We can definitely measure it. But what I am trying to say, that in case of spontaneous processes or natural processes or irreversible processes, we do not have to supply any work. We do not have to do work on the system for a spontaneous process taking place, right? So that's that. So for example, water kept at 150 degrees Celsius in the oven will vaporize. So it will continue to vaporize unless the surroundings are changed. If you change the surroundings in such a way that water starts condensing again, that is different issue. However, unless you change the surroundings, the process of evaporation of water that is kept at 150 degrees Celsius at 1 atmosphere per Celsius inside an oven, right? The oven temperature is 150 degrees Celsius. So if you do not change the surroundings enough, water is not going to condense at all, and water is continuously going to vaporize. For again, think of another case. Balloon, you fill the balloon with air and then keep it in a refrigerator. Now, if you are keeping it in a refrigerator, you will start seeing, you are kept in a refrigerator, what happens? The temperature of the balloon and temperature of air inside the balloon, both are going down, right? So, the temperatures have decreased. Now, I take the balloon and keep it outside. So, as soon as I take it outside, the balloon expands. Now, it expands. Now, again you bring it back to the refrigerator, it collapses. So, you change if you do not change the surroundings, it is not going to collapse. So, you can't tell that it's a reversible process. It's an irreversible process based on the surroundings that you have put in. So, for example, if you are putting the balloon in the refrigerator and then you are taking it out, it will expand. Now, that's actually, that expansion is inevitable. It has to happen. Now, you again change surroundings, then it can contract, right, or collapse, right? So, that is, so you can't say that since the balloon, based on the surrounding, the balloon has contracted or balloon has expanded, therefore, it might be a reversible process. No, the balloon, the process is still irreversible. Only thing that you are doing is changing the surroundings. So, so if I look at the second law's alternative statement, then one very good statement that comes in is, for a given system and surroundings, there is a natural direction for any process. There is a natural direction for any process. whether the process is curdling of milk, cooking of rice, aging of humans, whatever it is, you will have a natural reaction for any process, right? Given a system to the surroundings, or whether it is heat flow or whether it is mass flow. So the spontaneity of the process, if you want to define, we keep the system, it is fixed, surrounding is fixed for that system and surrounding. There is a natural reaction for any process. And as you can see, one of the very important and very famous quotes is that entropy is basically times error, right? Now, what does spontaneous process mean? So, I will talk about, again, we have given several examples. So, I will give yet another example. So, why is this that one of the process in one direction is spontaneous, in the other direction it is not? Because there is something called dissipation of it. Say, for example, when you bounce a ball, the ball bounces on the floor, on a hard floor. The ball bounces, again bounces, but every time it is bouncing to a lesser extent. And finally, at one point of time, the ball stops. And each bounce, the ball is losing its energy. And it is losing its energy or dissipating its energy as it bounces. Right? So, that is one very, very important thing that we have to understand about entropy. Entropy basically is a manifestation of the dissipation of energy. For example, another example, if we throw a stone in a pond, so when I am throwing a stone, I am imparting kinetic energy to the stone. Now, the stone comes in contact with the pond, which is like steel, water is still there. Immediately, as soon as the stone is striking the pond surface, you will see that the kinetic energy of the stone basically is getting dispersed in the form of water waves, right? It will form, and you will see these ripples that you will see. So, for example, here you can see the ripples that are happening. So, you have a stone, you have thrown it here, and then you can see the ripples. Now, think of the reverse process. All these ripples come together somehow, and it concentrates all the energy here, and the stone comes back to you. Now, that is a mighty difficult process. Means not difficult, it's an impossibility, right? It is naturally impossible, that direction. You can throw the stone and the stone's kinetic energy dissipates in the form of these water waves that form. Okay, initially the water was still, and then you have these water waves, but these water waves coming back in, so water waves are going out, right? They are going out in this direction. Now think of these guys are coming in. That seems not possible, and that is not possible. Why? Because that is not a natural process. Unless you do some stuff, you do a lot of work, these ripples are not going to come in and concentrate. See, that point that I am trying to make is that they will concentrate at the center. Now, this concentrate at the center to create enough energy that your ball comes back to you, or your stone comes back to you. That is not something that is going to happen, right? So, it is impossible. However, dissipation is like your energy is in some sense getting dispersed into various possible states. So, instead of remaining concentrated, it is getting dispersed. So, it is spreading all over. So, that basically leads to, this dissipation leads to a positive entropy production. And this dissipation is the one that basically tells whether the process is reversible or irreversible, process is spontaneous or artificial. So, this is something, remember, entropy, it's a very interesting subject, and it is also for material scientists because of this advent of this new class of materials which are high entropy materials. Again, there is a renewed interest in understanding entropy, but entropy is something that has always confused us, and we have looked at it from very philosophical points of view, but I am not going to discuss philosophical points of view here. I am going to discuss, if I know this definition of entropy, is it possible to use it in my scheme of things, like understanding all these founding principles in the context of understanding the properties of matter, and that is what I am going to do. So, now we continue. So, we have system, we have system here, we have surroundings here, and as you can see, entropy transfer, how does it happen? It happens because there is a heat exchange or energy exchange between the system and surroundings, and you see there is a delta S transfer that is happening towards the system, and there is a delta S transfer that is happening towards the surroundings, right? So you have, now look at surroundings. Now if I just think of surroundings alone, and again, for whether it is system or whether it is surrounding, in all cases what we can do, we can divide the change in entropy into two parts, right? One is the entropy transfer part, another is the entropy production part. That together, so these two terms together is giving me delta S surroundings. Similarly, for system, I can write this is delta S transfer for the system, and this is delta S production for the system, which gives you delta S. Now, one thing you have to understand is transfer business. So, basically, heat is exchanged. Say, for example, heat is input to the system from the surroundings, or heat is carried out from the system to the surroundings. In both cases, what is happening is entropy is transferred because of all this energy exchange, and as a result, delta S transfer system, and that's why I drew this arrow, that the delta S transfer system is negative of the delta S transfer in the surroundings. So that means delta S transfer system plus delta S transfer surroundings is equal to 0. So delta S universe, which is equal to delta S system plus delta S surroundings, is nothing but delta S production of the system and delta S production of the surroundings, because the entropy transfer term that happens between the system and the surroundings, right? If entropy is transferred from, say, system to the surroundings, there is also an entropy transfer from the surroundings to the system. As a result, the delta ST term goes to 0. So you have now delta SP over the system and the surroundings if I sum. Now, if you have delta SP, you have delta SP system and you have delta SP surroundings. Now, this as I told that this delta SP is the production, right? It's an entropy production term, which can either be, which in for natural processes is going to be greater than 0, and for both system and surroundings, but it can also be equal to 0 when the process is reversible. When the process is reversible, delta S universe, delta S system production equal to 0 for a reversible process. That is occurring within the system. Now remember, if a reversible process is occurring within the system, it does not necessarily mean that there is a reversible process that is occurring within the surroundings also. However, what I am telling is, if it is reversible, then that is the only case when delta S production term is 0. Otherwise, delta S production terms are going to be greater than 0. And that basically dictates, or that basically describes the natural direction of the process for a given system and surroundings. So, as I told again, so I am rephrasing again, that for a reversible process, again, that which you can plot and a PV diagram, a process that basically can be reversed, and it will just retrace the path back, and at every point of this reversible process, it's so slow, it's so infinite signal that every point the system and surroundings is allowed to take to come to equilibrium. Right? Now, as you can see, for a reversible process, whether it is system, whether it is surroundings, delta S production is going to be 0. Right? So that's right. Now you have, let us assume that delta Q rev. Okay, so we are writing delta Q reversal. So this is delta Q rev is nothing but delta Q reversal, and that is like the reversible heat input to a system, say for example, or heat absorbed by a system during an infinitesimal step in a reversible process, and let the temperature of the system be T. Now, as you know very well, that delta Q rev is a path function, right? It's a it is not an exact differential, unlike state functions. It means the amount of Q input or amount of Q input to the system or amount of Q extracted from the system is going to be dependent on the path along which the heat was transferred. Right? There are different ways to transfer heat to the surroundings or to the system, and it will now, if delta Q reversible is a path function. That means you cannot express it as an exact differential. And another thing, it does not depend on the final and the initial states. It depends on to find out the integral of delta Q reversible to get the amount of Q absorbed or amount of Q input to the system or amount of Q absorbed by the system. Then basically, in these cases, we need to know what is the path along which this heat transfer has taken place. And when I talk about this dispersion of energy in the form, see, one of the things is when I am throwing a stone, there is kinetic energy, and then there is this water waves there, and the final dispersion, the dispersion of energy that happens is in the form of, in general, it is in the form of thermal energy, right, or in the form of heat. Now, see a very interesting thing. Delta Q reversible, as you have seen, is a path function. It's a function that depends on the path of the process. But T or temperature is a state function that also we know. Now, S we define as a state function. Now, S is defined in a very interesting way. ds equals to delta Q rev by. So, there is a greater than ds is going to be exactly equal to, because it's a reversible heat transfer. Delta Q reversible is the infinitesimal heat transfer in a reversible process. Otherwise, there will be an inequality, right? So, that I will come to. But see the point that ds equals to delta Q reversible by. So, delta S, that is the macroscopic change, a measurable change, is equals to, you just have to take an integral from I to F, delta Q rev by T. Now, if I would have written this, so for example, I to F and delta Q rev is equal to Q, then this is completely wrong. This is utterly wrong. This is wrong. However, if I take initial and final state and I am writing delta Q rev by T and I am telling that this is nothing but I F ds, where S is supposed to be a state function. Now we have to understand why is it that ds equals to this one, where delta Q rev definitely is a path function. Why is it that delta Q rev by T is going to be ds or a state function? This basically, this is a delta Q rev by T itself is a measure of a state function, and that state function is nothing but entropy. So, we will consider a very interesting process, and these processes are called cyclic processes. Again, it's a cyclic process. We are not telling whether it is a reversible process, whether it's an irreversible process, but it's a cyclic process. What does cyclic mean? I start with initial, so that I have, you can see here clearly, you have an initial process. So, you start with this initial I, then you go to F, then you come back to I, and that is like, so from I go to F, from F I come back to I, and that is basically a definition of a cyclic process. Now, in such a cyclic process, if I have to evaluate this integral, okay, this is a cyclic integral or the entire cycle. From that means it goes from I, it goes to F, then F to I. So, this entire cyclic path you are evaluating the integral, then you will see that delta Q reversible. If it is a reversible cyclic process, if the cyclic process is reversible, that is all paths can be represented by a PV on the PV diagram, then delta Q reversible by T is integral of cyclic integral of ds, and as we know that it is going to be, so for example, if I go from I to F, the entropy change is SF minus Si. And then from F to I, it is Si minus Si. So you have two changes occurring. One is from I to F. So this basically SF minus Si is a change. And then again you go from F to I, Si minus SF. And as you can see, if I add it, the entropy change for this cyclic process is going to be 0. Right? For an arbitrary cyclic process, no matter the path, this is basically going to be Si minus Si. Right? If I add them together, it is going to be Si minus Si. Right? It becomes Si. So it is basically nothing but, if I write this way, it is basically nothing but Si minus SF plus SF minus, which is going to be equal to 0. Now we have to say formally why this delta Q ref by T is a state function. So for that we define a very interesting cyclic process, found in cyclic process, which is called the Carnot cycle. Okay, and we are telling from A to B, there is an isothermal expansion of volume, and from B to C, there is an adiabatic expansion of volume. From C to D, there is isothermal contraction of volume, and from D to A, it's a adiabatic contraction of volume, and finally you get an ABCD cycle. A, B, C, D, C. Right? It's a cycle. Now, as I told, A to B is reversible isothermal expansion, temperature T, and for isothermal, right? It's a fixed temperature. Let us assume the temperature is TH. Okay, and heat input is TH. Now B to C is a reversible adiabatic expansion. If it is adiabatic, then temperature can drop from TH. So here it goes TH. So it is from TH, it has gone to TC. But what about Q? Q is going to be 0. There is no heat transfer, right? It's an adiabatic process. Now you go again isothermal compression, right? Reversible isothermal compression at TC. So there is this temperature from C to D, the temperature is TC. It's an isotherm with the temperature TC, and then there is a heat released. This is something very important. The heat released is minus QC. And finally, from D to A, it's a reversible adiabatic compression. Temperature increases again. So if it is compressed, adiabatically compressed, the temperature increases from TC to TH. And you have completed the cycle. Now, if I just look at the entropy change according to the definition, let us assume that it is delta Q by T or Q by T. If that is so, then I will look at the entropy change. So here it is QH by TH, here it is QC by TC. A to B is QH by TH, B to C is 0 because it is adiabatic. So because it is adiabatic. And remember, this is isothermal with temperature TH, right? Hot. And then the CD isotherm has a temperature TC, right? Again, it's an isotherm with a different temperature TC. And so the entropy change in from C to D is QC by TC. Now, if you see D to A again, Q is going to be, means there is no Q, Q is going to be 0. And TC has now increased to TH. But if you look at the entropy change of this entire cycle, then what you find is that This is nothing but ds. In the cyclic integral of ds is nothing but qh by th plus q square. Now, as you know that for isothermal process, you have delta U, which is Q plus W, and since it is isothermal, CVDT, right? Delta U is basically CV delta T, but delta T is 0 because it's an isothermal process, right? Delta U is equal to 0. So, QH is going to be equal to minus WH. Now, what we tell reversible isothermal expansion. So, we can write WH equals to minus Va2 PdV. And now again we can assume that in the chamber that is undergoing the cyclic process, the cyclic process is undergone by a ideal gas fitted with a piston, say for example, and also the walls of this chamber are for the are kept either at a fixed temperature and at pH, and there is also TC, and for the adiabatic processes we are assuming that there is we are not assuming, we are enforcing that there is no heat transfer between the system and the surroundings, right? There is no heat transfer. Q is equal to 0. Now, as you can see, if I use PV equals to T, this is something that I have been doing for quite some time, and we are putting TH. TH is your isothermal temperature, so it becomes minus nRT H ln VA. Okay, therefore QH is nothing but QH is minus WH, which is nRTH ln VA. Now again, B2C is a adiabatic process. So VT to the power chi into equal to VC to the VT to the power chi. If remember, this is one very interesting thing that you are saying, VB into TH to the power chi and VC into TC to the power chi. Now you will tell how is this happening. How do you do that? So basically, instead of writing it as in terms of pressure, if you write in terms of temperature, then you will get this relation Tf by Ti to the power chi C by Nr, which is equal to Vi by V. Now you have for B2C one one adiabatic. So B2C is an adiabatic process. So it's an adiabatic process, and what is happening in B2C? Again, have a look at that. B2C, you have a adiabatic expansion. On the other hand, when it goes from D to A, it is adiabatic compression. Now you have adiabatic expansion, you have adiabatic compression, and you have now here when you did this, you wrote VB is here, right? This is your VB, and VB was at a temperature TH. VC was at a temperature TC. So you get VB TH to the power chi equal to VC TC to the power chi. As you can see, VI TI. So here it becomes VF TF to the power chi equals to VI TI to the power chi. That's what I'm writing. Now similarly from D to A, the same thing happens. Now what I'm doing is I am multiplying this way. I am multiplying this term. I take this term and multiply with this term, and I take this term and I multiply with this term. So in a crisscross way we are multiplying. So what we get is VAVC TH to the power chi is equal to chi, and this VVVB TH to the power chi is equal to chi. Or what you can write is VAVC equals to VVVB. VAVC, so that's what I have written. VAVC equals to VVVB. Or VA by VB equal to VD by VC. Now, if you see QC is equal to minus WC, that is again an isothermal process. That's an isothermal compression. From VC it has come to VD. Now QC, again the same formula if I write, and you are taking ideal gas, I get nRTC ln VA by VB. So QC is minus nRTC ln VB by VA. So QH by QC, if I do, so you have nRTH, QH is nRTH ln VB by VA, and this is minus nRTC ln VB by VA, which is nothing but TH by TC with a minus sign. See, remember there is a minus sign, and because so VY ln VY VA gets cancelled, so you have NR gets cancelled, so you have only TH here and TC itself. Now, if you have that, as I told in Carnot cycle, the cyclic integral of ds is QH by TH plus QC by TC. Now, QH by TH, according to this relation, QH by TH is minus QC by TC. So, it is, right, QH by QC equals minus TH by TC. So, QH, so if I take this guy here and QH by TH and this guy QH by TH and this guy here, so this becomes QC by TC and there is a minus sign and this is QH by TH, right? So QC has been taken that way. So basically you can easily see that. You can do it and see that minus QC by TC plus QC by TC which is become 0. So definitely for an ideal gas we have proved that indeed the cyclic integral of delta Q by T is going to be 0. So definitely we can see that it has, that means delta Q by T has to be a state function, right? Because it will depend only on the, as we told, that Si minus Si, the cyclic integral of ds is nothing but Si minus Si if S is a state function. Thus, we are proving that the quantity delta Q by T, remember, don't write it as D, let us not be confused here. Delta Q by T is cyclic integral of ds, which is 0, and we told that we insisted that S has to be a state function, but we are also showing just based on this Carnot cycle with ideal gas. But remember, there is one very small and interesting point here. We have proved that for a cyclic process, indeed delta Q by T, reversible cyclic process, delta Q by T indeed is 0, but for that proof we used a substance which is an ideal gas. However, we should prove that entropy is a state function irrespective of whatever substance we are taking, right? And that is something we can look at. Another thing that I want to tell you, that because of this cycle, and these cycles are sometimes used are basically used in heat engines. Heat engines are made of these cycles, right? They make use of the cycles to get some work done. So as you can see here, then we can define something called an efficiency of an engine. So this is an efficiency of a heat engine. And that is nothing but work performed by heat absorption, right? So it is mod of W, that is the work performed by heat absorption. Okay, so in the next class, we will go further into it and we will try to see whether it is true for general substances that entropy is indeed a state function, that we can prove, and it's a very simple and easy proof. So, and we will go from there in the next class. So, thank you, sir.